billion suns. Although all there will be up there at best is slime. It's just slime. Nothing.
A star blinked briefly, a fleeting event that most would overlook. But for astronomers, it was a critical clue. Something massive had just passed in front of it. Initial guesses pointed to a typical gas giant, perhaps akin to Jupiter. Yet as the data poured in, it became clear this was no ordinary planet. It was too large to be Neptune, too small to be Jupiter, and exhibited unexpected behavior. This was a Super Neptune, a rare category of exoplanets that scientists once believed were nearly non-existent. Then came more discoveries, forming a pattern that raised intriguing questions. Could these mysterious worlds be missing links in planetary evolution or something entirely unprecedented? The race to unravel their secrets had begun. A key breakthrough came in January 2025 with the discovery of two unique super Neptunes in the TOI-6054 system. These planets challenged previous assumptions with their unusual properties. Tight orbits. Unlike most super Neptunes, which orbit their stars over tens to hundreds of days, TOI-6054b and TOI-6054c complete their revolutions in just 7.5 and 12.5 days, respectively. Their proximity to their host star places them in the so-called hot Neptune desert, a region where planets of this size are rarely found, suggesting either difficulty forming or rapid degradation due to intense stellar radiation. Extreme temperatures. These newly identified planets rank among the hottest super Neptunes observed, further distinguishing them from prior discoveries. The findings hint at a potential shift in our understanding of planetary formation and evolution. As scientists continue to investigate, these enigmatic worlds may redefine what we know about the diversity of planets across the universe. One of the most striking features of the newly discovered super Neptunes, TOI-6054b and TOI-6054c, is their extreme temperatures. Unlike previously observed examples such as HP1b and GJ436b, which range between 500 and 1000 Kelvin, these planets are far hotter. TOI-6054b is estimated to reach around 1360 Kelvin, 1087 degrees C, while TOI-6054c hits approximately 1144 Kelvin, 871 degrees C. These scorching conditions place them among the hottest super Neptunes ever recorded. Such intense heat has profound consequences for their atmospheres. At these temperatures, atmospheric escape becomes a serious concern. Radiation from their star may be stripping away their gaseous outer layers, potentially transforming these worlds over time. This could explain the scarcity of hot Neptunes. Some may have started as larger gas giants but lost their atmospheres, leaving behind smaller, rocky remnants. But what if super Neptunes aren't failed gas giants? What if they're evolving into something entirely new? Another mystery lies in their density and composition. While typical super Neptunes resemble Neptune in our solar system, with a mix of gas, ice, and rocky cores, TOI-6054b and TOI-6054c show unusually low densities. This hints at a different internal structure, possibly dominated by hydrogen, helium, or even significant amounts of water vapor and other volatiles. These unique features might also reveal whether the planets formed close to their current orbits or migrated inward from more distant parts of their solar system. As scientists dive deeper into these findings, TOI-6054b and TOI-6054c could redefine our understanding of planetary evolution and the complex dynamics shaping exoplanet systems. The significance of the discovery. The discovery of TOI-6054b and TOI-6054c offers a rare chance to study planetary evolution under extreme conditions. Their tight orbits, scorching temperatures, and potentially unique compositions distinguish them from previously identified super Neptunes. This discovery provides valuable insights into key phenomena like planetary formation, atmospheric loss, and the long-term evolution of Neptune-like worlds in other solar systems. How were these super Neptunes discovered? TOI-6054b and TOI-6054c were identified using a combination of space-based and ground-based observation techniques. The process involved NASA's Transiting Exoplanets Survey satellite, TESS, and follow-up studies to confirm their existence, measure their masses, and analyze their compositions. Two primary methods were crucial: the transit method and the radial velocity method. The transit method and the role of TESS. The first signs of TOI-6054b and TOI-6054c came from TESS, a space telescope launched in 2018 to detect exoplanets around bright stars. TESS monitors large sections of the sky over extended periods, searching for periodic dips in a star's brightness. This technique, known as the transit method, works as follows. A planet passes in front of its star, blocking a small fraction of its light, and causing a predictable dip in brightness. If these dips occur at regular intervals, they indicate the presence of an orbiting planet. The depth of the dip reveals the planet's size, while the time between transits indicates its orbital period. TESS observed multiple transit events around TOI-6054, indicating two distinct planets regularly passing in front of their host star. The deeper dips suggested that these planets were large, consistent with Super Neptunes. However, at this stage, only the planet's size and orbit were known. Further confirmation was required. Confirming with the radial velocity method. To verify the transit signals and rule out stellar activity or background interference, astronomers used ground-based telescopes employing the radial velocity method. This technique helps determine an exoplanet's mass by measuring its gravitational effect on its star. Here's how it works. A planet's gravity causes its host star to wobble slightly as the planet orbits. This wobble affects the star's light, shifting it toward red or blue wavelengths due to the Doppler effect. By tracking these shifts, astronomers can calculate the planet's mass. Through this combined approach, scientists confirmed the existence of TOI-6054b and TOI-6054c and began unraveling their intriguing properties, paving the way for further studies on the evolution of exoplanetary systems under extreme conditions. Gravitational influence and planetary mass. Using high-precision spectrographs, scientists confirmed that TOI-6054b and TOI-6054c are massive super Neptunes. The combination of transit and radial velocity data allowed researchers to determine their size and mass, revealing insights into their density and possible composition. The gravitational pull these planets exert on their host star affects the star's motion, which in turn shifts its light spectrum slightly, a phenomenon known as the Doppler effect. By measuring these subtle shifts, astronomers can accurately calculate a planet's mass, proving that these super Neptunes are not just fleeting signals but substantial worlds. What does the graph show? The graph visualizes the brightness of a distant star over time. Each dip represents a transit event, where one of the planets crosses in front of the star, temporarily blocking part of its light. Key observations from the graph. Repeated dips. The consistent intervals of dips indicate that the planets are in stable, predictable orbits. Dip sizes. Larger dips are caused by a bigger planet blocking more light, while smaller dips correspond to a smaller planet. Observation consistency. Despite observations being taken months or years apart, the regularity of the dips shows stable orbits. This graph not only confirms the presence of the planets, but also provides essential details about their size, distance from the star, and orbital speed. Why do we find super versions of planets? Exoplanets are often described as super-Earths, super Neptunes, or hot Jupiters. This trend isn't because such planets are inherently more common but rather due to the way we detect them. Transit method sensitivity. Larger planets block more of their star's light, making them easier to detect. Smaller planets, like those comparable to Mercury or Mars, cause faint dips that often go unnoticed with current technology. Radial velocity sensitivity. Larger planets create stronger gravitational wobbles, making their presence more apparent through the Doppler effect. Learning more about super Neptunes. Super Neptunes occupy a fascinating space between Neptune and Jupiter in size. Understanding them is key to unraveling planetary formation and evolution. The James Webb Space Telescope, JWST, plays a crucial role in advancing this research. With its ability to observe in the infrared spectrum, JWST can analyze starlight filtering through a planet's atmosphere during transit events. This technique, called transmission spectroscopy, allows scientists to detect molecules like water vapor, methane, and carbon dioxide, revealing the atmospheric composition of these distant worlds. Future missions promise to further demystify super Neptunes, potentially transforming our understanding of planetary systems across the universe. JWST's role in Super Neptune research. The James Webb Space Telescope, JWST, not only analyzes the atmospheric composition of super Neptunes but also measures their temperatures and heat distribution. For planets orbiting close to their stars, this data is vital for understanding how intense stellar radiation affects their atmospheres. By observing atmospheric loss or expansion, JWST provides clues about why hot Neptunes are rare and whether some might evolve into smaller, rocky worlds over time. This insight helps scientists explore how planets adapt to extreme environments and what factors influence their survival. Complementary observatories and missions. While JWST leads the charge, other groundbreaking telescopes are set to transform the study of super Neptunes. Extremely Large Telescope, ELT, scheduled to begin operations in 2028. The ELT will directly image exoplanets, revealing details about their atmospheres and potential surface features. Ariel mission, European Space Agency launching in 2029. Ariel will focus on the atmospheres of hundreds of exoplanets, including super Neptunes, to identify patterns in their chemistry and thermal behavior. These advanced tools will complement JWST by broadening the number of planets studied and enhancing atmospheric models, forming a powerful network capable of answering key questions about planetary systems. What's next for Super Neptune research? JWST has already started delivering valuable data on exoplanets, with major discoveries about super Neptunes expected within the next 5 years. Ariel's mission will expand the research landscape, providing a large-scale survey of exoplanet atmospheres by the early 2030s. Together, the efforts of JWST, Ariel, and ELT will offer a comprehensive view of how super Neptunes form, evolve, and interact with their environments. The coming decade promises to be pivotal in unraveling the mysteries of these exotic worlds. Why it matters. Super Neptunes represent one of the most exciting frontiers in astronomy. Through advanced instruments, astronomers are beginning to uncover their secrets, from understanding how these planets form to exploring their atmospheric dynamics. These discoveries are reshaping our understanding of planetary diversity and inspiring new questions about what makes our solar system unique. As we continue to push technological boundaries, super Neptunes remind us that the universe is far more diverse and far more fascinating than we ever imagined. The next decade holds the promise of transformative breakthroughs that could redefine our place in the cosmos and pave the way for exploring even more distant worlds. If super Neptunes have taught us anything, it's that the best is yet to come.